बहुत हाई-फाई कर दिया सर आप। 3 मिनट में बहुत दिए। बहुत मेहनत कर रहे हैं। थैंक यू।
ओके, सो क्या आज अटेंडेंस थोड़ी कम दिख रही है क्या? तो एनीवे, we were looking at counting. That was the chapter that we were looking at. Especially we looked at how to establish binomial identities using counting. I gave you 2 examples. Of course, you can do it in many other problems. You can do in that way. Now, actually, we also looked at complexity problem, like finding the complexity of an algorithm, time complexity or space complexity. I give you only example of time complexity, right? The number of steps you count for executing an algorithm, right? Now, whenever we are doing these kind of things, many times because of the nature of algorithm, uh, when, when we want to compute the complexity, we end up with certain kind of relations known as recurrence relations. Okay, so in order to find the time complexity, I should know how to solve these recurrence relations. Okay, and so these recurrence relations are very important topic. So I will give you a brief overview of this recurrence relation today. What are the cases and so on, and later on, I will establish that after solving recurrence relation, one very important concept in complexity is master theorem. How to find out a general complexity if you know some recurrence relation. So anyway, those kind of things we are going to do. Now, coming back to recurrence relation, when we are looking at recurrence relation, how to solve? So something like an is equal to an minus 1 plus an minus 2. Okay, if this kind of relation is there between the numbers, how to find these numbers, right? You know what are these numbers? An is equal to an minus 1 plus an minus 2. Hemchandra numbers, right? Fibonacci to here near Patan, actually, that mathematician was there, Hemchandra. Okay, so, and as you know, Hemchandra numbers are quite useful if you go to US, and you know that here we use kilometer system, here we use miles, right? So you can convert miles and kilometers. You go, the initial point is 1, 1. The next Hemchandra number is 2. Next one is 3. Next one is 5. Then 8. And like that. So that means 5 miles is approximately equivalent to 8 kilometers. 8 miles is equivalent to approximately 13 kilometers. It's a very nice approximation, right? So as long as you move along the line of these numbers, you can find better approximation. So this will be quite useful if you have to convert miles in kilometers. Just walk along the line of Hemchandra numbers, or now sometimes they are also known as Fibonacci numbers, because Fibonacci introduced them into the Europe. Anyway, so that is thing. So let me give you one very simple example. But these recurrence relations are very, very useful. And actually, if you remember, you might have seen how to solve ordinary differential equation with constant coefficients. You remember anything about it? d2y over dx2 plus dy by dx or something like that, right? d2y over dx2 plus a1 dy by dx plus a2 y is equal to some function, right? Remember solving these equations? Calculus किया है कि नहीं? Online है तो we know कि the status, right? So mostly it is copy paste, right? Because of online business, I know. Anyway, so those equations, if you remember how to solve, We assume that the solution is of the form e raised to power m mx. You substitute e raised to power mx into the equation, solve for m, known as auxiliary equations, and using auxiliary equations, you find the roots of the equation, right? Those kind of stuff, and then you solve the equation, right? The similar approach here we use for solving recurrence relations. Okay, so we assume the solution is of the certain form, and then we try to solve the auxiliary equations. Let me give you the general theory about solving recurrence relations. Today we are going to focus on recurrence relations. Okay. Suppose, look at a petri dish. You know what is petri dish? These are some bacteria, bacterial colony. And we know that initially there are only 5 bacteria. And every hour they double. Amount whatever is there at a given time, every hour it doubles, right? So if I ask you how many bacteria after n hours, so how will you answer this question? Okay, in this petri dish there are certain number of bacteria, initially 5 bacteria. Of course I've drawn some more, but that's okay. Every hour they double. So after n hours, how many bacteria? If I have to calculate this, so suppose after n hours I have an bacteria, right? An is this number. Then we know that an is equal to 2 times an minus 1 is positive, and a0 is equal to 5, right? An is equal to 2 times a minus 1 because bacteria doubles every hour. So this relationship is there. Initially we have 5 bacteria, so I can solve this recurrence relation, right? How will you solve? I mean, one way is you just substitute a0, you get a1, and you get a2 using a1, then get a3 using a2, and so on, right? You can clearly see that a power is going to come, right? Some sort of power is going to come, right? So basically, before giving you how to solve these equations, let me consider another recurrence relation. An is equal to 2an minus 1 minus an minus 2, and is equal to 2, 3, 4, and so on. So just like that, differential equation is given to you. Suppose differential equation is given to you, and a solution is given to you. You say that somebody says that check if this is a solution. You substitute that value y into the differential equation, and if it satisfies the equation, it is a solution, right? Same thing with algebraic equations as well. Similarly, here also, if some solution is given to you, or somebody tells you, your friend will tell you that okay, an is equal to 3n is a solution. What will you do? You substitute this, right? 2 times an minus 1 minus an minus 2 is equal to 2 times 3 times n minus 1, 2 times 3 times n minus 1 minus 3 times n minus 2, okay, is equal to 3n is equal to an. So we started with 2 times an minus 1. So one side, right hand side, we substituted this value and we got 3n, which is an. So it is satisfying the equation, right? So an is equal to 3n is a solution. Now I want to check whether an is equal to 2 raised power n is a solution or not. Can you tell me if it is a solution? Just substitute and check whether it is a solution. So what is your answer? No. A 2 times an minus 1 minus an minus 2 will be 2 raised power n minus 2 raised power n minus 1, which is not is equal to 2 raised power n, right? So this is not a solution. Fine. What if I give you that an is equal to 5? Is this a solution? N is equal to 5. It's a constant sequence. It turns out this is a solution, right? So just by substituting the value of an in the equation, you can verify if it is a solution or not, right? Very simple thing, just like differential equations or algebraic equations, right? Ax square plus bx plus c is equal to 0. A is not equal to 0. Your favorite questions, right? So I hope you are still finding the solution. Anyway, now I can write down the general a most general form of the equation is recurrence relation is an is equal to c1 times an minus 1 plus c2 times an minus 2 plus dot 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 ck times an minus k. So c1, c2, c3, ck, all these ci's are real numbers and ck is not equal to 0. Ck is not equal to 0 means what? It is ensuring that we have equation of degree k. Degree is k. First of all, note that this is a linear equation, right? So there are no terms which are multiple, like we don't have terms like an into an plus 1, or the product of these ai's are not there, right? It's a linear equation, right? It's a linear combination kind of thing, right? C1, C2, C3 and the linear combination is equal to an, right? So an equal to, this is the linear combination of ci's, right? So basically ci's are scalars, right? Okay, so it's a linear combination kind of thing. It's a homogeneous linear equation. And degree k. So here you can see that an is expressed as in previous k terms. An is expressed in previous k terms. Okay. Since ck is not equal to 0, the degree is k. If ck minus 1 is not equal to 0, बाकी ck 0 होता तो फिर degree क्या होती? K minus 1, right? Whatever is the highest is non-zero. Okay. So if I have to solve this equation, so in the case of differential equations, if you remember, we assume that the solution is of the form y is equal to e raised power mx, right? You substitute e raised, why we assumed e raised power mx? Because the differentiation of e raised power mx will give you multiples of e raised power mx itself, right? That's the argument. I mean, that was the thought process in order to find out a solution for ordinary differential equation with constant coefficients. Here we have homogeneous equation. So what kind of solution we should seek? An should be E का बिजनेस तो नहीं है यहाँ पे, क्या होना चाहिए? Right? We seek solution of the form an is equal to r raised to power n. We want to check for some r, can I have solution like this? Okay. And now what? Basically, I can substitute an is equal to r raised to power n in this expression and solve for r, right? Just like that, we substituted e raised to power mx in the differential equation case. Here I am substituting this in the recurrence relation, right? An is equal to r raised to power n. So an is equal to r raised to power n is a solution if and only if r raised to power n is equal to c1 r raised to power n minus 1 plus dot 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 ck r raised to power n minus k. So this is known as characteristic equation or auxiliary equation. Just like that, if you compare analogy with differential equation with constant coefficients, there we used to have auxiliary equation in M. So now, in order to solve the equations, R is unknown. R, we need to find the value of R. If I know the value of R, I know An because An is equal to R raised to power n, right? Now, since this is a equation like this, I mean, again, I'm going to look at first a simple case to illustrate you the concept how to solve. I will take degree 2, right? So that it is easy to get the solution. So in fact, I'm going to mention a theorem. Suppose C1 and C2 are real numbers. And suppose R square minus C1R minus C2 is equal to 0 has two distinct roots. This is the auxiliary equation, right? R1 and R2. Then the sequence An is a solution of the recurrence relation An is equal to C1 An minus 1 plus C2 An minus 2 if and only if An is equal to alpha 1 times R1 raised to power n plus alpha 2 times R2 raised to power n. And alpha 1 and alpha 2 are constant. So now you can see that I am looking at degree 2, like so basically simple case first rather than looking at the general case. This equation has solution this, a combination of powers of R, and this is something you can compare with roots of the equation. In differential equation, there are two roots. One solution will be e raised to power m1x, another one will be e raised to power m2x, right? If you remember those things, I'm just trying to refresh your ordinary differential equation thing. So, so solution is something like this, okay, for this equation. So basically from this equation, we substitute an is equal to, not for this, from here, we substitute an is equal to r raised to power n. We get that kind of equation, right? You solve it, and then after solving, we get the answer, right? There are two roots. So basically, now this equation, r square minus c1r minus c2, may have distinct roots, r1 and r2. Single root repeated twice, all those conditions will come, right? So what will happen in each case when we are solving the recurrence relation? That is the important thing. So now I am going to prove one part of this, only one portion. And second part, what will you do? It's a T problem. So at least you should also try something, right? So let me try to establish. So I have to prove this if and only if condition. If this is given, then this, if this solution is given, of course, it will satisfy the recurrence relation, and vice versa, right? Every solution of this recurrence relation is of this form only. So let me give you proof of one part. Of course, proof of the part 2 is written in the notes, but I would suggest you try, because thinking is very, very important, than memorizing. Anyway, so first claim 1, if an is equal to alpha 1 raised to power r1 raised to power n plus alpha 2 raised to power r2 raised to power n, then an is a solution. How to prove this? We know that r1 and r2 are roots of the equation r square minus c1r minus c2 is equal to 0, right? So this implies that r1 will satisfy this equation, r2 will satisfy this equation. We have r1 square is equal to c1r plus c2, and r2 square is equal to c1r plus c2. Why? Because both r1 and r2 are solution of this equation. They will satisfy this equation. I have written that, right? They will satisfy this equation. Fine. Now I consider c1 times an minus 1 plus c2 times an minus 2. I have to see that this is a solution. So what is c1 times an minus 1? c1 times alpha 1 r1 raised to power n minus 1 plus alpha 2 r2 raised to power n minus 1 plus c2 times alpha 1 raised to power alpha 1 times r1 raised to power n minus 2 plus alpha 2 times r2 raised to power n minus 2. सिंप्लीफाई करके कितना आएगा ये? Alpha 1 r1 raised to power n minus 2 times c1 r1 plus c2 plus alpha 2 r2 raised to power n minus 2 c1 r2 plus c2. Now c1 r1 plus c2 from here r1 है, sorry, हाँ? अरे मेरे से भी गलती हो जाती है यार. I'm also a human being, right? So anyway, so this is there, right? So c1 r1 plus c2 is what? r1 square, and this is r2 square. Essentially you get the answer, right? Just by calculating. So if an is of this form, then it is a solution, right? This is something. Let me do a couple of examples. So the part 2, claim 2, I left for you. And when I said I left for you, it may come anywhere in quiz or exam. तो आंसर देखा जाए तुमको पहले से मालूम है, पेपर, क्वेश्चन पेपर. Solve. A0 is equal to 2, A1 is equal to 7. Can anyone tell me what is the solution? How to solve it? Characteristic equation लिखो. R square, अभी जो लिखा है ना, just do it. हाँ? The characteristic equation is r square minus r minus 2 is equal to 0. You solve it, r is equal to 2 and r is equal to minus 1. These are the roots, distinct hai. So n is the solution if and only if n is equal to alpha 1 times 2 raised to power n plus alpha 2 times minus 1 raised to power n, right? I've just substituted the value. Now initial conditions are given, so I can enumerate these constants. Alpha 1 and alpha 2 I can find, right? We have A0 is equal to 2 is equal to alpha 1 plus alpha 2. A1 is equal to 7 is equal to alpha 1 times 2 plus alpha 2 times minus 1. If we simplify, alpha 1 is equal to 3, alpha 2 is equal to minus 1. So An is equal to 3 into 2 raised for n minus 1 raised for n. Got it? R1, R2, those values are there, right? So just like the differential equation, actually it is essentially the way you do the differential equation. The only thing is the route, now the little bit structure is changed, right? But just behaves in that. I think first time when you saw differential equation, you must enjoyed it because I think it's very easy subject, right? I remember I was not introduced differential equation in 12th actually. First time I saw in my BSc, Bachelor's of Science, and then I scored full marks in that paper. It was very easy. So I think you might have, and I mean you might have seen that it's very easy subject, right? Of course, if you look at fractional differential equation, then there is a problem. You know what is fractional differential equation? Differential equation involving fractional derivative, right? So differentiating real number of times something, right? So we don't have these kind of auxiliary equation business also there abhi tak. Nobody has discovered. Maybe you can work on those problems. How to solve fractional differential equations, right? Anyway. Second problem. Solve. These are Hemchandra numbers, right? The initial condition 0, 1. Can you solve using the same technique now? Write down the auxiliary equation or the characteristic equation in terms of R square. So roots of the equation I need to look at R square minus R minus 1 is equal to 0. R1 is 1 plus root 5 by 2 and R2 is 1 minus root 5 by 2. Here solving this equation by Shridharacharya formula is very easy. So if something can be solved, I don't like, should be over Z4, Z5, then only you like it, right? So now, using the above theorem, Fn is equal to alpha 1 times 1 plus root 5 by 2 raised to power n plus alpha 2 times 1 minus root 5 by 2. Where alpha 1 and alpha 2 are constants. If you use the initial condition f0 is equal to 0 and f1 is equal to 1, we can solve. And I leave it is an easy exercise, right? You can solve for alpha 1 and alpha 2, right? So we have done one example. Now the second example, I leave it for you, right? Just substitute these values and solve for alpha 1 and alpha 2, right? I hope you can do that. Not a difficult thing. Now, if you look at the characteristic, so we saw one case of the characteristic equation of degree 2 in the case when there are two distinct roots R1 and R2. Then the solution is of this form, right? Right? alpha 1 times r1 raised to power something plus for 2 times. Now what happens if equation has only one root? C1 and C2 are real numbers. C2 is not equal to 0. Suppose r square minus C1r minus C2 is equal to 0 has only one root. R naught. Now if you remember what happens in the case of differential equation, if there is only one root, so one root is e raised to power mx, second is certain times, right? If you remember, right? Same idea here, nothing else. Then an is a solution of the recurrence relation. An is equal to C1 an minus 1 plus C2 an minus 2 if and only if an is equal to alpha 1 times r naught raised to power n plus alpha 2 times n times r naught raised to power n. So remember this n times this quantity is the first one and the second one. So of course you will ask for proof. So if you look at in the notes, I have written it's a cup of tea, right? You can take a cup of tea and try to establish this. It's not difficult. कैसे करोगे? You substitute करो and then show that it is a solution and the reverse way. It's fine. I can give you one example actually, so that you know what is happening. Solve. An is equal to 6 an minus 1 minus 9 an minus 2. A0 is equal to 1 and A1 is equal to 6. Obviously, this will give you auxiliary equation r square minus 6r plus 9 is equal to 0. This implies that r is equal to 3 is the only root. Therefore, an is equal to alpha 1. An is equal to alpha 1 times 3 raised to power n plus alpha 2 times n times 3 raised to power n. Now, if you use initial condition a naught is equal to 1 and a1 is equal to 6, you will get a naught is equal to 1 is equal to alpha 1, a1 is equal to 6 is equal to alpha 1 into 3 plus alpha 2 into 3. This gives you alpha 1 is equal to 1 and alpha 2 is equal to 1. So an is equal to 3 raised to power n plus n times 3 raised to power n. Right? So all this very easy. As long as you have done a good differential equation course, this is very easy, right? Look at the recurrence relation, solve for the auxiliary equation, form the auxiliary equation or the characteristic equation, solve for r, the roots are distinct, you know what is the solution form. If the roots are not distinct, if there is single root, then you know how to write down the solution, right? बहुत बोरिंग लग रहा है ना, कुछ लोगों को नींद आ रही है. Anyway, this is kind of routine thing, It is end meeting warning. I do. Strange. Now, whatever we have done for degree 2 can be done for degree k. If the roots are distinct, the solution will be what? You can just mention the result without saying anything. C1, C2, Ck are real numbers. And suppose the characteristic equation is r raised to power k minus C1, r raised to power k minus 1. minus dot dot minus ck is equal to 0 has k distinct root r1, r2, rk. Then the equation an is equal to c1 an minus 1 plus c2 an minus 2 dot 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 ck an minus k has a solution an of the form alpha 1 r1 raised to power n plus alpha 2 r2 raised to power n plus dot 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 alpha k r k raised to power n. So I mean, I don't know why there is a problem. Anyway, this is alpha 2 raised to power r2 raised to power n and so on plus alpha k raised to power r k raised to power n. General case, right? Not very difficult. If the roots are distinct, you know what to do. So I think now I am going to write down a very general result now, multiple root theorem. There is no need to look at all the proofs at this moment, it's okay. C1, C2, Ck are real numbers. Suppose characteristic equation is r raised to power k minus C1 r raised to power k plus, k minus 1 minus dot 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 minus Ck is equal to 0 has t distinct roots r1, r2, rt with multiplicity m1, m2, mt. So root r1 appears m1 times, r2 appears m2 times, and so on, right? Certainly, m1 plus m2 plus mt is equal to k, because that has to be the total degree. Then the recurrence relation an is equal to c1 an minus 1 plus ck an minus k has an as a solution if and only if an is equal to alpha 1 0 plus alpha 1 1 n alpha 1 m1 minus 1 n raised to power m1 minus 1 r1 raised to power n dot 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 alpha t0 plus alpha t1 n alpha t m t minus 1 n raised to power mt minus 1 times rt raised to power. This is most general form. Basically, the idea is when we multiply with n, then the power of that n square and so on, right? In general, the most general form. Obviously, intuitively, it should be clear that this is the case, but it requires a proof. Proof you can skip for this case. So I hope when you do a couple of problems, you will memorize how to do these things, right? Many times when you are trying to memorize, normally in 12th, what you do in CBSE board or any other board, just memorize the formulas and apply. But that is not a real mathematics, right? Because you don't get any beauty. Beauty you get here, right? In these kind of things. Anyway, so this is the general solution. So you might have observed whatever we have done till now. is a homogeneous equation. It's a homogeneous equation. Now, what was homogeneous equation in the case of differential equation? d2y over dx2 plus whatever constant times dy by dx plus certain constant times y is equal to 0. If its right hand side is 0, it's a homogeneous equation, right? But on the right hand side, if there is a term, say some function, sin x, cos x, they put, then it's a non-homogeneous equation. And how you used to solve it? First you solve homogeneous equation, then you find the particular integral, and then add them, and you get the solution. The similar result holds here also. Again, I'm not going to prove anything. I will just state the result, and in a counterintuitive manner, you know, because you know the differential equation thing. I'm assuming that you know the differential equation business. So it's really easy to establish the answer here. So I'll just state the result and maybe one example. So equation of the form an is equal to 3an minus 1 plus 2n. Now this term is making it non-homogeneous, right? Because of this term. So in general, an is equal to c1 n minus 1 plus dot 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 ck an minus k plus some function of n. If this is not equal to 0, of course, all ci's are real numbers. By the way, I should tell you the beauty part here, right? So right now I am assuming these AIs, the coefficients are, these CIs are real numbers. What happens if they are from Z2, Z3, Z4, Z5? Beautiful things will come out of it, right? So be ready for that beautiful thing sometime. And I'm sure you will not find solution. So that is the case anyway. So given a general equation like this, if I look at only this equation, C1 an minus 1 plus Ck an minus k. So this is your associated homogeneous equation. Homogeneous recurrence relation. So we call it as AHRR. Associated homogeneous recurrence relation, AHRR. So let me give you one result. So remember, how do we solve? So in order to solve this equation, what I do, I look at the homogeneous equation, look at the auxiliary equation or characteristic equation, solve for those RIs, R1, R2, or whatever roots are there, and write down the solution. And if you are able to find one particular solution of the general solution, just add it. The similar method works here, and you get the solution. Okay. Let me give you the result. If ANP a particular solution of non-homogeneous linear recurrence relation with constant coefficient an is equal to c1 an minus 1 plus dot 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 ck an minus k plus some function of n. So for this equation, if we have ANP is a particular solution which is satisfying the whole thing, right? Then every solution is of the form is sum of these two things where ANH is the solution of the associated homogeneous recurrence relation an is equal to c1 an minus 1 plus dot 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 ck an minus k. Okay. So this is the general result, works exactly in the similar manner. So you look at the non-homogeneous equation recurrence relation. From that, you form a associated homogeneous recurrence relation, which that Fn part is 0. Solve it using auxiliary equation or characteristic equation. Find the roots. Roots could be R1, R2, whatever, Rk with certain multiplicities, right? Or Rt with multiplicities. So first root occurs M1 times, second M2 times, and so on, whatever. Then you have the general solution, how to write general solution of the homogeneous equation. And then somehow you find one particular solution, add it to the homogeneous equation, homogeneous solution, and you get the answer for the whole thing, right? That is a key idea. It's a beautiful thing, right? I mean, the technique is very popular. So I'm going to do just one example, and I think that should be last thing for today. An is equal to 3an minus 1 plus 2n. A1 is equal to 3. You have to solve for this. Associated homogeneous sequence relation is, right, when 2n part is 0, right? You are assuming that this is associated homogeneous sequence relation. You can solve it. This is alpha times 3 raised for n. Alpha is a constant, right? Now, by trial, we seek particular solution of the form an is equal to now how to solve this particular solution. I mean, here also we do trial and error. We seek solution of the form n plus d. Is this a solution? Substitute, so Cn plus d is equal to 3 times Cn minus 1 plus d plus 2n. This implies that 2 plus 2c time n plus 2d minus 3c equal to 0. So this implies that you can solve the two equations, right? You will get c is equal to minus 1 and d is equal to minus 3 by 2. So by this trial business, we found that particular solution is minus n minus 3 by 2. Therefore, general solution is an is equal to an particular solution plus homogeneous solution is equal to minus n minus 3 by 2 plus alpha times 3 raised for n. Got it? So something very simple. So I hope you saw this when you go over Z2 or Z3, solve these equations. Beautiful things are observed, really. I can tell you. You will observe beautiful things which are, they could be useful, for example, in generating random numbers, all kind of things, So I think that's interesting stuff. But I think, of course, it is not part of your this thing, but you can think about it. So I think that's all about recurrence relation. Now I think in the next class we are going to look at the master theorem. Okay. So I gave you overview. So I am again summarizing. If there is a recurrence relation of degree k, right, homogeneous or non-homogeneous. If it is a non-homogeneous, you first solve for the homogeneous equation, find the roots and so on, R1, R2, R3, whatever. Write down the solution and add it to the particular solution of the whole equation. That is the whole idea. Exactly similar to differential equations, what you have seen, right? The only thing is that थोड़ा सा स्वरूप अलग है बस, right? Rest everything is same. Yes. No, so see, the character of this equation depends on these CIs. Right now we are taking CIs in real numbers, right? Yeah. So basically, in fact, I would like to mention now, if you take CIs to be in the Z2 or because see, ultimately it will lead to a equation over Z2, and then you know what happens there, right? So it's very easy. So maybe now you are thinking the next quiz could be based on that, right? Recurrence relation. But that is, I think, in the future, I don't know. Anyway, thank you.